here's our normal modes, and there's one mathematical point I want to make sure we're all okay on before we move on to more physics. And that is the temporal frequencies and the spatial frequencies. So we got a new parameter we're going to talk about a lot. So first, let's recognize that this is the times part and this is the space part. So I'm going to draw a line here to separate the two. And we're pretty good with the time part. Since you've thought about oscillations a lot, even in earlier physics, you thought about the period. T is the period. And the unit of a period of an oscillation is, the x-axis is time, right? For an oscillation in time, the unit is seconds. But what the period really is the seconds per cycle. You don't usually think about the per cycle part, but that really is, technically that's what it is what is the time it takes to go through an entire cycle is t. And you're also good at thinking about f, which is 1 over t, which is the frequency in hertz. We're all familiar with frequency simply in hertz, which is, just invert this, cycles per second. Okay. And then once you get to slightly more grown-up physics, you eventually accept the angular frequency. You realize we don't care about cycles, we care about radians. We keep up with a cycle as 2 pi radians, and you begin to accept omega as 2 pi f as the angular frequency. If you haven't accepted that yet, I'm not sure how you made it this far in this class. It's the angular frequency, and it is in radians per second, where a cycle is just 2 pi radians. Radians per second, okay? So now, what we want to be sure is that we all are okay with the same thing to happen in space. Right? So if we plot this cycle in space, here's y. So in our case, we're making waves. We have some wave shape here. And the equivalent of the period you know very well. Actually, it is just lambda. It's the wavelength. You may never have thought it that way, but lambda is, of course, the wavelength. But really, it's the meters per cycle. So lambda is in terms of meters or nanometers or whatever. But really, just like the period, it's the meters per cycle. And that's pretty much what you use a lot in early physics. You don't go much further than that. But technically, we could follow this analogy and have something called 1 over lambda. We don't talk about that one much. It doesn't really have a letter I can give it. But it's basically a spatial frequency. Some old textbooks assume a certain letter means 1 over lambda, but it doesn't anymore. It's a spatial frequency, and it would be in cycles per meter. But we don't use that. What we do is jump straight to the radian version of this, and that is k. That's what I'm here to tell you about. K is 2 pi over lambda, because instead of cycles per meter, we care about radians per meter. Okay, so this has a special name, the wave number in radians per meter. Okay, it's just 2 pi over lambda. So you may have seen it before. K is 2 pi over lambda. I just want you to understand what it is, why it is, where it came from. It's because we like to do things in radians in physics. Radians per second is omega, radians per meter. The spatial part is k. So we could replace this with kn. In some books, you might see this written knx. Anytime in a sinusoid, you have k times the x and you have omega times the t, is the sort of grown-up way to write it. But you can write omega over v. It doesn't matter. Okay? But anyway, that's what k is. And the name wave number is because it's literally the number of waves per meter. How many waves? This many waves. Cycles would literally be counting the waves. Radians per meter is counting the radians per meter. But that's what it means by wave number. It is actually the number of waves that you can fit in this amount of space.